Okay, so hi everybody. I know it's a little primitive, but I tried to put together a little presentation to discuss that last question of the lab that I'd ask you to focus on. And what I wanted to start with, and the question was, of course, what's another way that you could find the concentration of an unknown substance without using the graph that we produced? And you still have to use a graph similar to the one that we produced, but I'll get back into that a little bit later. I did want to talk about what you can see here on this one image that I scanned in of what is an actual spectrophotometer. Now our colorimeter, we had spectrophotometers, I just used the colorimeters because they're a little simpler. I think they mimic what happens in this original big box. So the thing that you're seeing here is called a spectrophotometer. There's actually some stored in the classroom, and it consists of a place for you to put your cuvette, a place to adjust things like the amount of light and the wavelength, and you can read off of this analog dial here what the absorbance is. But what I'd like to focus on is like a schematic of what it looks like actually inside. So maybe let's take a look down at the picture here at the bottom. So whether it's a colorimeter or a spectrophotometer, you have to have a light source. Then what will happen is that the light is being transmitted, light of a particular intensity, towards your cuvette. The intensity of the light is detected in this detector and then registers as a particular amount of absorbance that you can see on that dial on the far right. And essentially that's what we did with our colorimeters in this schematic sense. So let's take a look then at the next document that I want to pick up to try to understand how we can use something called the Beer-Lambert law. Now, I'm not sure if I can make this a little bit bigger. So let's see if I can make it a little bigger at first so you can see it a bit better. And this is the thing I want to focus on first. We have an equation here that's called the Beer-Lambert law. And that stands for, capital A is absorbance. You could have measured transmittance, and there's an equation that connects those two. Remember, transmittance is the light that will pass through, absorbance is the light that's being absorbed. So we're going to stick with absorbance just to keep it simple. Now you have three other letters. Remember I said that it was A, B, C. So when you look at the three little letters, this first guy is kind of an oddball. That one's called the extinction coefficient, I think is one term for it. It's also called molar absorptivity. Spell that one. Come back to that one a little bit later. B stands for the length of the pathway. And typically that's the distance that it took from going from one side of the cuvette to the other side of the cuvette. And classically they make the cuvettes like 1 centimeter in length because that makes for a lovely number when you have to do the calculations. So that's our pathway. And C stands for the concentration. Now I'm going to come back out of this a little bit and show us what this graph is presenting. If you look at the horizontal axis, just like we had the independent variable be concentration, so does this experiment. This is one done with iron ions. These work well with metallic solutions of ions that have unique colors. So iron's got kind of a yellowy orange color. As you saw, the copper ions have a bluish color. They're measuring in a different unit of concentration, but I think that's relatively irrelevant. And then over here, on the vertical axis, you're measuring absorbance. So someone constructed here with known concentrations of iron ions a graph that plots concentration versus absorbance. So far, exactly the same as what we've done. Now what we need to do is to use some algebra to be able to figure out what is that little letter A, the extinction coefficient. Because we can measure, and I'll go back into zooming up here. You guys have to be patient with me. I can get this technology, but I'm slow. So I can measure the absorbance coming through the machine when I put a particular known concentration in there. So that means I'll know A. I know how wide my cuvette is, so I know B. And finally, I know the concentration that I made of that particular substance. So I have four values, three of which are known, and the fourth one I could find through simple algebra. So you could do a little bit of algebra where you could solve for the little letter A, the absorptivity or extinction coefficient. And of course, small letter a would be equal to absorbance divided by the quantity of B times C, pathway times concentration. So for a particular solution of something, you could calculate what's its absorptivity constant or extinction coefficient. So now having done that, let's pretend that we had an unknown. Let's pretend we had this time that the absorption I would know because I measured it off the machine. I had calculated the extinction coefficient because I had done so from a previous trial where I had calibrated it with known concentrations. I still know the length of the pathway through which the light has to pass on the cuvette, and the unknown is that puppy, concentration. So another way that you could solve for concentration of an unknown, assuming you know little letter a, is now take some algebra and letter C, concentration, should be equal to capital letter A, absorbance, divided by the quantity of small letter a times B, extinction coefficient times the pathway length. So that's really pretty much all I wanted to talk about on this lab. And the point of doing this was I did truly want you to understand what's happening inside the guts of the machine. And you should have noticed then, as we increase the concentration of any solution, you're going to see the amount of light being absorbed increase. You could just have easily graphed concentration versus transmittance, and I hope you would logic out that the more and more concentrated it is, the less light would be transmitted if that's what we were measuring over here as the dependent variable. So that's the ABCs of the Beer-Lambert law, or sometimes called Beer's law, and I have always seen a question about that on the AP exam in either the free response section or in the multiple choice. Okay, it should be enough there for you to process that last question, and I'm expecting you guys to turn in the graph that you printed out, the pre-stamped lab procedure with the title and the objective, and a response to that last question that I posed to you and asked for you to research. That should be it. Take care, and I'll see you at the next vodcast.